Hey everybody, welcome to week 4 of a field guide to particle physics. We've been talking about exotic and wild things like neutrinos and muons for a while now, and I thought it would be nice to kind of reconnect with something that's a little bit more familiar or intuitive for everybody, namely light. So, episode 4, Photons. Let's get started. Going outside, whether it's for a ride or a hike or a run, or even just a walk, requires you to be attuned to your environment. On the road, there's going to be cars. In the woods, there's going to be animals. And on the mountain slopes, there's all kinds of objective hazards that you need to pay attention for. We engage the world around us through our senses. Our vision relies on light, and our hearing relies on sound. What is the difference between sound and light? Well, sound is actually pressure waves moving through the air. Sound bounces off hard surfaces and gets muffled by softer ones. It carries energy away from whatever is making the noise. Higher volumes of sound typically means more energy.
A higher pitch typically means a smaller item.
And a lower pitch typically means a bigger item, so
Consider like a jet fighter flying in the sky versus a chipmunk hiding in the tree. Sound is energy that's moving through the air. Where there is no air, like in outer space, there is no sound. But what about light? Light is kind of a different story. It's perfectly happy moving through empty space. We know this because we can look up to the sky and see the stars, really, really far away stars, and even our own sun. An astronaut on a spacewalk outside the space station may not be able to hear anything outside of their spacesuit, but they can certainly see the Earth below their feet. Light, too, carries energy away. After all, lamps need electricity to function, flashlights need batteries, hot things glow brightly, but they fade away as they cool down. Light is carrying energy away from those things which shine. But this presents a question. If sound is energy moving through the air, what about light? What is light moving through? A lot of smart people throughout history have asked this question. And the best answer, at least for a while, has come from a simple observation of looking through the window of your house at night. From inside the house, you can see the streetlights outside, maybe even the moon or the stars. You can shine a flashlight through the window if you like, just to get a better view. But some of that light always reflects back at you. In addition to those streetlights, you can also see your kitchen lights, your laptop screen, your reading lamp. It's not perfectly reflected. Only about 4% of the light that's emitted gets reflected back at you by the glass. As it turns out, this kind of partial reflection of light is really best explained in terms of waves. But just as sound waves have air and ocean waves have water to move through, what stuff is light waving through? What is the substance that's doing the waving? Some folks will tell you that the answer is nothing, and that it's some kind of great, amazing observation in the history of physics or whatever. That light doesn't need anything to shake or wiggle through. It's supposed to be some kind of a big deal. But that's kind of a disingenuous framing. It's kind of like a conflict of ideas between the older things like phlogiston or aether hypotheses conflicting with more modern perspectives on light. A more honest answer starts with a slightly different question. The energy in sound waves is carried by the motion of particles in the air. What is the energy of light waves carried by? This one is easy enough to answer. The energy in light waves is carried by the electric and magnetic fields. Electric fields. Charges have them. We push electrons around the wires in our house with them. Modern society relies on them heavily. Magnetic fields. Well, as you recall, the Earth has one. Many refrigerators have worn them. Magnetic fields come from electric charges that are on the move. Sometimes, like refrigerator magnets, the movement is subtle. The charges that are moving are the electrons and the protons in the molecules that are actually spinning. Fields, like electric and magnetic fields, are definitely a modern concept. The main idea here is that fields are sourced by electric charges. The fields are how these charges communicate with each other. For example, protons repel each other because their electric fields do the repelling. Because both electric and magnetic fields are born of electrically charged particles, we tend to call them electromagnetic fields. One big insight into electric and magnetic fields is that these fields can act as sources for each other. Electric fields can source magnetic fields, which in turn can source electric fields, which in turn can source magnetic fields. These are electromagnetic waves. In other words, this is how light works. Wait, so light is electromagnetic waves? What? Yes. A quick and easy way to make an electromagnetic wave is to take some kind of electric charge and shake it violently. Because the electromagnetic waves radiate away from the shaking charge, we sometimes call these waves electromagnetic radiation. Now, there are two characteristics of electromagnetic radiation that are worth describing. The first is frequency, and the second is spectrum. Frequency is easy. Waves wiggle. How quickly those waves wiggle is the frequency. The frequency of wiggles can vary a lot, from really, really high frequencies to really, really low frequencies. Spectrum is a harder thing to quantify. Spectrum is kind of noisy. Light doesn't come out clean. It usually comes out as a mess. By a mess, I mean light usually comes out in a mixture of different frequencies. To see how that works, consider hot things. Hot things glow, but why do they glow? They glow because they're full of things like atoms with electrons that are banging around. As we increase the temperature of these things, they bang around faster and faster and faster. And that is what temperature is, after all, the moving and shaking of atoms in a material. But if you can get things hot enough, that movement and shaking of electric charges will cause those items to glow. So what's the color of that glowing light, of, say, those stovetop coils? Is all the light that's coming out just orange? Well, no. Just like all the cars on the highway are not going exactly 60 miles an hour, and all of the coffee that you order at Starbucks doesn't come in cups that are exactly 12 ounces full, or that just how there aren't exactly 1.93 children in every American home. What is 0.93 of a child anyway? Orange is kind of the average frequency of the light that's coming from a stovetop coil. Light is really an admixture of individual light waves with different frequencies. Incidentally, this is how things like prisms work. They separate out the different frequencies of light from each other. Now, this study of light, so-called optics, is a long and complicated story in its own right. We've talked a little bit about, say, refraction when we discussed the movement of muons through ice sheets in Greenland and Antarctica. We won't get into much more detail about optics than that here, except for one last thing. I want to make sure to talk about the entire spectrum of light waves. Light frequencies range from the really, really fast wiggles to the really, really slow ones. The length of a wiggle in light as it moves through space is called the wavelength. Some light wiggles or oscillates only a few times per second, and one of those oscillations for the light wave can be about 60,000 miles. Remember, the speed of light is super fast. It moves at something like 300 million meters per second, which is like 186,000 miles per second. So 60,000 miles per wiggle is a relatively slow oscillation. Some light wiggles 3 billion times per second. The amount of distance that light would travel between those kind of wiggles is closer to 6 centimeters, or maybe like half a foot. That's considerably faster. But in the grand scheme of things, all of those types of frequencies are still pretty low as far as light is concerned. Those are all radio waves. Yep, radio waves. Things like radio, radar, microwaves, they're all different forms of light. Light with really slow frequencies and really long wavelengths. Visible light, the light that you're probably most familiar with, has wavelengths that are between 400 and 700 nanometers. That's roughly about the size of a biological cell. Considering that radar spans something like 60,000 miles to just 6 inches, visible light is just a tiny portion of the light spectrum. Between radar and visible light, there's, of course, the infrared. But really, who sets all these crazy labels and definitions of light based on, infrared, X-rays, radio? Like, what's the meaning of all this? And ultimately, it boils down to the function of how those wavelengths, that part of the spectrum, interacts with matter, interacts with us. Different frequencies of light do very different things. So let's do a quick review of the major ones. First, radio. Radio is for ideas. Radio waves are associated with really long wavelengths, as we've discussed. They're good for carrying information, but they don't interact very strongly with things. And in the grand scheme of things, they're generated by relatively slowly wiggling particles. If you increase the speed of those wiggles, that frequency of oscillation, from radio, you get into the spectrum known as the infrared. Infrared is for heat. Infrared light is all around us. Have you ever felt the heat given off by a pan that you pull from the stove? Or maybe radiating off the sidewalk or the road after a summer sunset deep in the heart of Texas? That heat that you're feeling is actually a form of light. It's infrared light. Thermal imaging cameras capture light in the infrared. Visible light is for biology. Visible light has a much higher frequency than the infrared. It's pretty good at generating wiggles in the electrons of biological molecules. Our eyes, for example, can see visible light, and photosynthesis in plants happen because visible light is captured in their chloroplasts. Ultraviolet light burns. Ultraviolet light wiggles even faster than visible light, and it's a little more destructive. It can damage biological cells. If you've experienced sunburn, you can blame ultraviolet light coming from the sun. On the high frequency end of the ultraviolet spectrum, ultraviolet light is actually used to sterilize water and surfaces. X-rays demolish. On the extreme end of the spectrum of light, with really high frequency oscillations of the electromagnetic field, we find ourselves with X-rays. X-rays appear to penetrate living tissue much more easily than a lot of other forms of light. For example, they're really great at diagnosing broken bones. They also appear to do a lot of damage to tissue that they flow through. And it's with X-rays where light begins to look a lot more like nuclear radiation. The electromagnetic wave model for light really does a good job of explaining a lot of the phenomena that we see. Indeed, trying to explain partial reflection of light through glass is really hard to do without the concept of waves. But you see, here's the thing. There's been a number of physical experiments that contradict the wave hypothesis of light. To see how these contradictory experiments might work, let's imagine an experiment. Suppose you have a light source and shine it at some kind of detector. Something that makes a little bit of noise whenever it detects some light. At first, the detector is just constantly crying out. It's just a loud, all-encompassing noise. But let's suppose that you slowly turn down the intensity of light. The detector starts to get more and more quiet. And you might figure that this will just go on forever. As you decrease the intensity of the light, the volume will just continue to decrease. Less light, after all, means less noise coming from the detector. But eventually something different happens. As you keep turning that intensity down, the low hum of the detector starts to kind of break up like static. It eventually breaks into individual clicks. Eventually, you only get one distinct pulse at a time. And this is not a quirk of your experiment. If you got something that was way more sensitive to light, you'd see exactly the same thing at exactly the same intensities. This is something that Einstein got his Nobel Prize for. Light, like all other forms of matter, it seems, is made up of its own kind of atom. These individual particles of light, as it were, are called photons. It's not really a great analogy, but a beam of light coming from a light bulb or something is a bit like water flowing in a river. It's the collective motion of a whole bunch of different water molecules together. Electromagnetic waves, as it turns out, is just the collective motion of a bunch of different photons. The reason that this analogy is not a really good one, though, is even more confusing. You see, the partial reflection of light, that wave behavior that we see when looking through glass, happens at the level of individual photons. To see how this might happen, you can repeat the same experiment we just talked about, but put a pane of glass in between the detector and the light. When you first turn on the light, both detectors go nuts. But as you turn the intensity of light down, both detectors start to grow quiet and quiet and quiet. Eventually, once again, you're starting to count individual photons of light. But see, here's the thing. 96% of those photons appear to go through the glass and meet that detector. And the other 4% reflect from the glass and make it to that detector. But as you turn the intensity even further and further down, so you're just kind of shooting one photon at a time, it's a little more strange. As it turns out, that photon, as it's released from your light source, has a 96% chance of making it through the glass, and only a 4% chance of reflecting from the glass. And there's no real way to explain it other than just sheer probability. It's as if the photons are behaving like waves themselves without any kind of collective behavior. And this is why people struggle to fully understand photons. They defy a simple explanation as a particle or an electromagnetic wave. It's probably not a surprise that photons really don't fit in with our normal intuition about things like particles. Normal particles have a mass and they can move around and they can slow down. You can stop them. You can put them in a box. You can carry them around. They can smash into each other and bounce off of each other or against the walls, kind of like billiard balls. That's our intuitive picture of particles anyway. But light, photons, not so much. They never stop moving. They never stop moving at the speed of light. They're always on the go. You can't really put photons in a box. So if photons defy our attempts to characterize them, what's the best way to start describing them? Well, one reasonable place to start is with their energy. The energy of a photon is directly proportional to its frequency, the kind of rate of those wiggles in the electromagnetic fields. That constant of proportionality is always the same, no matter what the frequency is, for every single photon in the universe, as far as we can tell. In a very real sense, that constant of proportionality kind of sets the scale for the quantized, granular particle nature of light, as it were. So photons are little packets of energy characterized by their frequency. So let's check in with the electromagnetic spectrum and see how this all fits together. Radio. Radio is for information, right? No big deal. Very low frequencies, very low energy photons. Of course, you can always have a lot of those photons put together, as in radio antennas, but individually they're not so bad. And that's great because our world is bathed in radio waves. If you carry a mobile phone, you are constantly exposed to them. But those photons, very low energy, no big deal. Infrared light has a higher frequency than radio. There's a lot more energy per photon there, and that energy is what we understand as heat. Great, okay, so let's keep turning up the dial. So visible light has even higher frequencies and therefore more energy than infrared light. And when things get really, really, really hot, they start to glow. And now we have a good understanding as to why. Really hot things have more energy to radiate, and they're radiating, vibrating at a higher frequency. So visible photons with higher energies are produced. And maybe now you can see how ultraviolet light can produce sunburns. Those photons are much higher in frequency and therefore are much higher in energy. They can actually damage biological tissue. This is exacerbated, of course, by the really high frequency and therefore really high energy photons from the spectrum of X-rays. They have an incredible amount of energy packed into a single photon. In some sense, they really do act like billiards bouncing off your bones. So putting all this together, we see something that's kind of interesting. The higher the energy of the individual photons, the more they tend to behave like actual particles, like the billiard balls. But in reality, photons need to really get up enough frequency or enough energy to really kind of break apart the individual atoms or molecules that make up our everyday experience, to really be thought of as particles or billiard balls or whatever. So you're probably wondering at this point, what does this all have to do with electric and magnetic fields and charged particles and so on? Like, okay, we get it. Photons are what comprise electric fields, magnetic fields. But what does a photon have to do with an electrically charged particle? Charged particles, like protons or electrons, can catch or throw photons and absorb or exchange their energy. That's how those particles communicate. That's how they interact. To see how this works, let's take a look at the hydrogen atom. Do you remember the orbitals that we talked about earlier in the helium shortage? They came out with some regularity, 2, 2, 6, 2, 6, 10, etc. These correspond to distinct energy levels for an electron orbiting any atom, but in particular the hydrogen atom. When an electron catches a photon of a certain energy, it bounces up to a higher energy state. This is unstable, and so if left to its own devices, it usually decays down to a lower energy. This is a very similar mechanism behind particle decay that we've been discussing. This is quantum mechanics. Sometimes, depending upon the details, these decays are something of a delayed effect. If you've ever seen that eerie green glow from kind of like a glow-in-the-dark item or glow-in-the-dark paint, you've seen this effect in action. The probability of decay for these electronic states for kind of glow-in-the-dark stuff is just a little bit lower, but it still can happen, so it definitely will happen. It just takes a little bit longer time. If you have a really pure material, say like hydrogen gas, you can do a reasonably good job of extracting out those individual colors from those individual electron energy levels. It's when you have a whole mass of different kinds of chemicals and different kinds of stuff that it all tends to kind of blend together into one uniform glow. Things become a little less clear. So light, the photons buzzing around the room with you, they're all emitted in this kind of quantum mechanical probabilistic way. If you throw a bunch of photons at an electron, there's also a probability for absorption. Sometimes it's a high probability, so it happens rapidly. It all depends on the material. Sometimes it's high, like visible light is with our eyes, and sometimes it's really, really low, like high-frequency infrared light, which can travel right through our skin, which incidentally is how those heart rate monitors like Fitbit or the Apple Watch work. They detect blood oxidation levels in your blood through your skin because near infrared, that is to say infrared light that's kind of near visible red, our skin is completely transparent to it. A lot of these ideas we've encountered already in our study of particle physics. Particles like the muon or the neutrino have a very low interaction probability, and so they just move straight through a lot of stuff, straight through the atmosphere, straight through a large chunk of the Earth, straight through us. But alpha particles, protons and neutrons, they have a pretty high probability of interaction, so they really don't get very far. So let's put these probabilistic interaction ideas together with our earlier discussion about the partial reflection of light of photons through glass. The photon, as with any other particle, has a certain probability of interacting with other particles. They can be caught, they can be thrown, they can be even reflected, kind of depending on the details. Sometimes only part of a photon's energy will be absorbed by an electron, say. The rest of the photon then just kind of bounces away. For the specific case of visible light and glass, the likelihood then of the photon being reflected by the glass is about 4%. The rest of the time it just kind of passes straight through. The rules governing the calculation of those probabilities for light interacting with other matter are actually not too hard conceptually to compute. They just involve a whole lot of counting. But they can be done and they can be explained, for example, to folks in a really skinny book. Well, okay, what have we learned? Electromagnetic waves, or light, is made up of photons. The frequency of the light determines the energy of the individual photons. Different colors correspond to different frequencies and therefore different energies. And visible light makes up only a tiny fraction of the entire spectrum of light, from infrared and radio waves on one end to ultraviolet and X-rays on the far other extreme. The colors of light coming off of different objects that we see in our day-to-day life kind of depend on the chemical makeup of those objects. The molecules in those chemicals all have different discrete energy levels that can catch or throw photons of different discrete energies. This molecular game of catch is a probabilistic one. It's a quantum mechanical one, and it's how charged particles interact with each other. In a companion video to this one, we'll talk about applications of these ideas to things like chemistry and astronomy and just reality. But I want to leave you with one final thought for today. Remember how we discussed that the higher the energy of a given photon, the more it tends to behave like a traditional particle, kind of like a billiard ball. Well, as things turn out, this fact is true for particles of all kinds, even for particles that have a mass. For photons, for light, that relevant energy was something around the ultraviolet, where it could really start to break apart molecular bonds. The energy threshold for particle behaviors for other kinds of particles really depends on the context. For electrons, it's whatever the binding energy of that electron is to the atom or molecule to which it's tied. When its energy, or frequency if you like, are below that certain threshold, the electron is just kind of smeared out as a standing wave, like on a drum, surrounding the nucleus of the atom. When it has enough energy to break apart from that atom or molecule, that's when it really starts to behave like a particle, or a billiard ball. For the neutron, the same thing is kind of true. Neutrons with very low speeds tend to kind of fuzz out a little as well, which makes them a little more susceptible to being absorbed into other nuclei. But when neutrons are moving very, very quickly, they tend to behave a lot more like bullets, even, or particles, billiard balls. A good general rule for other flavors of particle is that when those things are moving really, really, really fast, they behave like a traditional particle, or like a billiard ball. When they're moving slow, less so. The wave-like quantum mechanical nature of those particles tends to dominate. So all particles, regardless of size, scale, or mass, have a wave-like nature to them. That nature is tied through quantum mechanics to a probabilistic interpretation of how they interact with each other, which ultimately lays down kind of the general architecture for how particle physics works, period. Okay, that was the big ideas behind photons and how electromagnetic waves work. Next time, we're going to apply those ideas to things like chemistry, to things like astronomy, and things like the birth of the universe.